In this video, we're going to consider geometric sequences and series, which is another type of progression that we need for the A-level course in mathematics. So geometric sequence, just like the arithmetic one, we denote the first term as a letter A. But this time, instead of adding a number to get from one term to the next, we're going to times by a number. And the number we times by is denoted by the letter R for the common ratio. So therefore, the second term is going to be A times R, which can be denoted as AR. And then the third term would be AR squared, times by R again, etc., etc., AR cubed, AR to the 4, until you get to the general kth term, AR to the k minus 1. And we call it the kth term because I can't call it the rth term because R is now used as the common ratio. And we keep going until we get to the last term, the nth term of the sequence, which is AR to the n minus 1. And it's n minus 1 because we started with AR to the 0. So we're going to finish at n minus 1. This is the nth term, so there are n terms in the sequence if it stops. It might be infinite, and we'll consider infinite cases in another video. Okay. So what letters we got going on here? A is the first term of this sequence. R is called the common ratio. So an arithmetic sequence had a common difference. Geometric has a common ratio. You divide one term by its previous, you will get R. K is your kth term. And we'll get to the formula for that. We'll be using that throughout this video. And then N is the number of terms in the sequence. Okay, so if it terminates, there'll be a finite number of terms. If it's infinite, then obviously it carries on forever. Okay, so the formula for the kth term, as denoted at the top of the page there, we've got AK is AR to the k minus 1. So if you want the fifth term, plug in k is 5. If you want the 20th term, plug in k is 20. If you want the 2036th term, plug in k is 2036 into this formula. It's not given to you in the formula booklet. You need to learn this one, and we'll be using it throughout this video. Okay, so it's a general kth term of a geometric sequence. Okay, so quick look at some specific geometric sequences before we delve into some examples. So what we're going to do for these ones is just have a look at them and decide what is the value of R and what is the value of N. So we can see that to get from one term to the next, we're going to be multiplying by the number 2. All of these are geometric sequences. So therefore I can state that R is 2. And then this one, well, this is the last term because we can see you've got an ellipsis and then a number after it. So this is AR to the n minus 1. So that's going to be 1 because the first term is 1 times 2 because the common ratio is 2 to the power of n minus 1 is equal to 1024. So we can solve that. I'm going to solve it on the calculator, but for this case, you might even know this one because it's quite a common one. It's quite an easy one, powers of 2. But the way we would solve it is, well, we divide by the 1, we're going to log base 2, and then we're going to add 1. So it's going to be log to the base 2 of 1024, and then you need to add 1 because that would be n minus 1. So it's 11. Okay, and a quick sanity check, 1 times 2 to the power of 11 minus 1 should give us our 1024 back, which it does. Okay, so that's the R and N value for this one. Okay, this next one, we can see that we're now times it by -3. So R is -3. We can see it's negative because we get alternating terms. So positive, negative, positive, negative. That happens when you have a negative R value. And that's absolutely fine. It's still geometric. This time we can't log to the base -3 of this one. So you just log to the base 3. And the math will sort itself out because if it was an odd term, then this would be negative. So you just ignore the negative and n would be odd. And if this was an even term, then it's positive, which it is here. And the log to base 3 would sort it out. So log to the base 3 of 13,122 divided by A in this case is 2. So I've got to divide that by 2. And then don't forget to add 1 So I get that n is 9. And again, you can check that. If I do 2 times -3 to the power of 9 minus 1, you should get that 13,122 back out again. Okay, so we have negative r value. You could have a decimal r value. Doesn't have to be an integer. This one, the terms are halving each time. So the common ratio then is a half. That's absolutely fine. And then n, well, we're going to have log to the base of a half, which is obviously absolutely fine. You can do that. Of 0.3125 divided by a, and a was 20. Okay, the first term was 20. And then don't forget, of course, to add 1 to that. So we get n is 7. Another way to do it, to check, 20. And then if I do answer divided by 2, that's term 2, 3, 4, 5, 6, and 7. Okay, there you go. 7th term is 0.3125. So you could do that way to check it if you wanted to. Okay, 2 more quickly then. This one, to get the common ratio, it's not as easy to spot as the previous ones. If I take any term and divide it by the previous term, I will get the value of r. So in this case, if I do 108 and divide that by 324, I will get that the ratio is a third. And that would be the same for any term divided by its previous term. So if I do 36 and then divide that by 108, I will also get a third. Or if I do 12 divided by 36, I will still get a third. So r is a third. And then we have an ellipsis, and then there's nothing afterwards. So that means for this one, n is infinite. Okay, there are an infinite number of terms in that sequence. Okay, and finally this one here. We start with 7, and we're going to finish at 1,708,984,375. The common ratio is 5. I'm going to times by 5 to get from there to there. And it's got to be that same constant multiplier, otherwise it wouldn't fit the geometric definition. So r is 5, and now I need to log to the base 5 1,708,984,375 divided by a, which was 7. Don't forget to add 1, is 13. Okay, and that's it. All right, so those are some specific geometric sequences and their r and n values. Okay, so let's have a look at some example questions on geometrics. Example number 1. A geometric sequence is given as 16, 24, 36. Part A, state the common ratio of the sequence. Part B, find the 5th term. And part C, which is the first term to exceed 1,000. Okay, so to get the common ratio, we're going to take any term and divide it by its previous term. And the reason why that works is because this one would be denoted as AR, and this one is A, and this one is AR squared. So if I divide this by this, I'll get AR squared divided by AR, which is just R. Or if I take this and divide it by that, I'll get AR divided by A, which is just R. So whichever term you do, if you divide it by its previous term, you get R, the common ratio. So for part A, R is going to be 24 divided by 16, which of course we should simplify that. So 8's going into those, so that's 3 divided by 2. Okay, so it's a common ratio of 1.5. Okay, part B. Find the 5th term. Okay, so we could then take this 36 and times it by 1.5 twice more. That would be absolutely fine. But I'm going to say that the 5th term, A5, is going to be A, which is 16, the first term, times by R, which we know is 1.5, to the power of 5 minus 1, which is 4. Okay, that will give us our 5th term. So 16 multiplied by 1.5 to the power 4 is 81. So there we go. Our 5th term is 81. Okay, and then part C, which is the first term to exceed 1,000. We could go through this manually, times by 1.5 each time until we get to a term which is bigger than 1,000. I'm going to do this algebraically. So what we want is AR to the k minus 1 to be greater than 1,000. plug in our A and R values. So we're going to get 16 times 1.5 to the power of k minus 1 is greater than 1,000. That is now an equation which only contains k as an unknown. Oops, 1,000. So divide by 16 and log to the base 1.5. So k minus 1 is greater than log to the base of 1.5 of 1,000 over 16. Okay, and the inequality remains the same direction, and that is okay because the base is bigger than 1. If the base was less than 1, then we would have to reverse the direction of our inequality. So that means we require k to be greater than log to the base of 1.5 of 1,000 sixteenths. And then don't forget to add your 1. Okay. So we can plug that into the calculator. Log to the base 1.5 of 1,000 sixteenths plus 1. So we need k to be bigger than 11.19 blah blah blah. Now as a number that would round to 11, but of course we need k to be bigger than this, so 11 does not satisfy that. Therefore the first term to exceed 1,000 is the 12th term. Okay, it's the 12th term. All right, the 11th term is not big enough. And if I calculate the 11th term, that's 16 times 1.5 to the power of 11 minus 1. That is smaller than 1,000. And then the next one, which is 16 times 1.5 to the power of 12 minus 1, that's the 12th term, that is bigger than 1,000. So the 12th term is the first one to be bigger than 1,000. Okay. All right, that was example number 1. Example number 2. The first term of a geometric sequence is 162. Given that the third term is 24 more than the next term, and that all of the terms in the sequence are positive, calculate the common ratio of the sequence and list the first 5 terms. Okay, so let's first of all break it down. We've got the first term is 162. So that tells us that A is 162. So state that. Okay, now the third term is 24 more than the next term. So that'll be the 4th term. So A3 is A4 plus 24. Okay, the third term, A3, is 24 more than the next term, which is the 4th term. Okay, so I take the 4th term, add 24 to it, and I get to the 3rd term. Okay, so that's that information there in an equation. All right, so I've now got enough information to calculate my R value, because I know that A3 is AR squared, and A4 is AR cubed, and then I've got my 24, but I also know that A is 162. So this is actually a cubic equation in R. So I'm going to get that 162 R cubed, subtract 162 R squared, plus 24, must be 0. Okay, that's plugging in 162 in for A, and then rearranging it so all of my powers of R are on the left-hand side. Now what I could do, of course, is simplify that, because I can see that the coefficients are all multiples of 2, probably even higher numbers as well. But I don't care about that. What I'm actually interested in is the values of R. So if I go into my equation solver on my calculator, I can solve this polynomial equation. It's a degree 3 because it's a cubic. The coefficient of R cubed is 162. There's no R term, so the coefficient of R would be 0. R squared is negative 162, and then the constant there is 24. And I get, I have an R value of 2/3 appearing twice and negative 1/3 appearing once. So the solutions to this are R equals 2/3, 2/3, and negative 1/3. Okay, so those are my 3 solutions that I get. However, there's something in the question which allows me to eliminate them. All of the terms in the sequence are positive. So that means I can reject that. So that means that R is 2/3. All right, I've now got A and I've got R. I can now define my sequence. So I can do the first part and list the first 5 terms. So we know the first term is 162, and then to get the next term, we just times by R. So back into computation mode, start with 162, answer times 2/3. So that's 108 is the next one. 72 is the next one. 48 is the fourth one. And the fifth and final one is 32. And there we go. Those are the first 5 terms of my sequence. All right. You could do a quick timeliness check. The first term is 162, and the third term is 24 more than the fourth term, and all of the terms are positive. So that fits everything given to me in the question. So it's good. All right. Geometric series. So just like any other series, a series is the sum of a sequence. So the geometric series, denoted S subscript n, is the sum of the first n terms of a geometric sequence. So for the arithmetic case, what we did was we took the first and last term and added them together, and that gave us something constant, and then the second and penultimate term, and that gave us the same thing. That's not going to work for the geometric one. We're going to try a different tact for this. This is not something that you need to know. The formula that I'm going to derive now is given to you in the formula booklet. You do not need to know its derivation for this course, and you don't even need to learn the formula because it is in the booklet. So the way to get the formula that's given in the booklet is to take this definition of Sn and multiply it by R. So R times Sn. So I'm going to take all of these terms and times them by R. So that's going to become AR, that's going to become AR squared, that's going to become AR cubed, plus dot dot dot. That's going to become AR to the n minus 1, and then that's going to become AR to the n. Now what I do is I'm going to subtract one from the other. So if I do Sn subtract RSn, what we'll find is that the AR in Sn cancels with the AR in RSn and the A squared. The A cubed will cancel there. The AR to the n minus 2 would cancel with the previous one. The AR to the n minus 1 would cancel there. And I'm left with this A term at the beginning of Sn and this AR to the n term at the end of RSn. So that's going to be A subtract AR to the n. Now see if I make Sn the subject. So if I factorise out the R, so 1 minus R into Sn is A into 1 minus R to the n, and then divide by this coefficient of Sn. That's going to give me that Sn is equal to A into 1 minus R to the power n divided by 1 minus R. And that is the formula for the geometric series. Okay, this is given in the formula booklet, so you don't need to learn it, which is good. Just to be able to use it. This is obviously a true statement for any R value except for R is 1. If you plug in R is 1 into this formula, then you'll get 0 over 0. So it actually breaks down at that point. But if you had a geometric series with R is 1, that's actually just a constant sequence. So you wouldn't use this formula for it. You would just do n times R. And that will give you the n times A. And that will give you the sum. So yeah, this is the formula that works for any R values that are not 1. All right, example 3 then. A geometric sequence is given as this thing. Calculate the sum of the sequence. So we can see it's finite because it finishes at a number. We don't know how many terms there are yet. Okay, we're going to use our trick from earlier in the video to get the n value, and then we can plug in our A, R, and n into this Sn formula, which is in the formula booklet. So first of all, let's calculate the value of R. So to get from there to there, times by R. So if I do that divided by that, I'll get R. So R is going to be 1,750 divided by 1,250, which is 1.4. And of course, we could check that by doing the next one as well, just to make sure that we didn't do anything stupid on the calculator. So the third term divided by the second term is also going to be that same R value, which it is. So that's good. R is 1.4. Now we need to calculate the which term this is. So AN, the nth term in the sequence, that's going to be A times R to the power of n minus 1, and we know that's 9,411.92. So we can solve this equation for n, and that gives us how many terms there are. So log to the base 4, sorry, log to the base 1.4 of 9,411.92 divided by A. Okay, so I've divided by that, logged both sides. That's what n minus 1 equals. So to get n, I need to add 1. It's 7. Okay, there are 7 terms in my sequence. Quick check, always worth checking. A times r to the power of n minus 1 should give me that number, actually does. So that's good. All right. So n is 7, I've got r is 1.4, I've got a is 1,250, so I can calculate Sn. So S7 then is a into 1 minus r to the power n divided by 1 minus r, that's the formula that's given. A in this case is 1,250, that's the first term in the sequence, times by 1 minus r is 1.4, to the power of n, which is 7, divided by 1 minus r. This is all numerical, so I can just pop it all into my calculator. So 1,250 times 1 minus 1.4 to the power 7 divided by 1 minus 1.4. I get 29,816.72. And that is the answer. So sum of the first 7 terms. Okay, on to my fourth and final example. So this one is my hard one of the video. This will differentiate your A's from your A-star students. Okay, so 3 times the second term of a geometric sequence is 180 more than 7 times the fifth term. Given that the third term is 2,880, calculate the sum of the first 6 terms. All right, there is so much going on in this question. Let's just break it down bit by bit. So first of all, 3 times the second term, okay, well that is 3a2, that's 3 times the second term of a geometric sequence, is 180 more, so 180 plus, 7 times the fifth term, so that's going to be 7a5, okay. 3 times the second term is 180 more than 7 times the fifth term. All right, so that's that bit of information down as an equation. Second bit, given that the third term is 2,880, so that's A3 equals 2,880, calculate the sum of the first 6 terms. Okay, what we've got here is we've got a pair of simultaneous equations. All the AKs, so A2, A5 and A3, those are all expressions in A's and R's. So we can eliminate A to get R from these, and then hence get A. So this one is AR squared. That tells us that A is 2,880 divided by R squared. Okay. Right, and this one here, well, A2 is 3AR. Okay, the second term is the first term times r. That is 180 plus 7 times the fifth term, which is 7ar to the 4. Now I can use this definition of a in here, and that'll give me a polynomial in r. So I'm going to get 3 times 2,880, which is 8,640. Times r divided by r squared, so that's divided by r. Okay, that's me plugging in the a there into the a there, that gives me this term. There's no a in there, so that just remains at 180. And then I've got this term in here, that's also an a, so I'm going to get 7 times 2,880, and that is 20,160. And then I've got r to the 4 divided by r squared, so that's an r squared. Okay, so that gives me this equation. It looks a bit messy because I've got r's in the top and bottom, but actually if you sort it out, it is just a cubic equation in r. So what I'm going to do is times the whole thing by r, and then just rearrange bits. So I'm going to get 20,160 r cubed plus 180r subtract 8,640 equals 0. Okay, just like before in example 2, I could simplify that, but I'm not interested. I just want to find the values of r from this equation. So it's a cubic equation. I'm going to go into my equation solver, which is that mode there, my calculator. It's a polynomial, so f2, degree 3, so f2 again. And this time the coefficient of r cubed is 20,160. There is no r squared term, so that's a 0 in there. 180 for r, and then negative 8,640 there for the constant. And that only gives me one r value. There is only one. This is a cubic equation. It could have 1, 2, or 3 solutions. This one only has 1. If you were in a complex mode, so I'm currently in real mode, if you were in a complex mode, you might see a couple more solutions, complex solutions, but we're not interested in those, okay? Geometric sequences at this point, we only look at real numbers. So r then is 3/4. Okay, that's the only value of r. We can plug that into here then to find a, because a is 2,880 divided by r squared. So back into computation mode, 2,880 divided by 0.75 squared is 5,120. Okay, all right, I've got my a and I've got my r. That is now going to define my sequence. Now the question, calculate the sum of the first 6 terms of the sequence. Okay, so now I've got r, I've got a, I know that n is 6. I can then calculate this. So S6 then, that's going to be a, which is 5,120, times 1 minus r to the power n, divided by 1 minus r. Okay, that's the formula taken from the formula book and plugging in r is 3/4, a is 5,120, and n is 6, to give me the sum of the first 6 terms. Back to the calculator, 5,120 times 1 minus 0.75, so 6, divided by 1 minus 0.75 is 16,835. Okay, and that is the sum of the first 6 terms. If you wanted to, you could, of course, write out those 6 terms. Make sure that all of this information from the question is indeed true. So 3 times the second term is 180 more than 7 times the 5th term, and the third term is 2,880. And then you could add up those 6 terms to get the same answer, just to double check. It is all true. Feel free to go check that yourself. That ends my video on geometric sequences and series. The next video is the last one on the sequences and series section, and we're going to look at what happens if we have an infinite number of terms in a geometric sequence. Thanks so much for watching. Please check out any other videos you might need help on in your A-level mathematics studies, and drop any comments below if you have any questions.